So there is an input voltage, and if that input voltage somehow is amplified and you get a gain and you get to see a voltage at the output, this is, let's say, output voltage. So if it is within the limit of Vmax and Vmin, it's not clipped. But if it is not within the limit, then we'll get to see, clips. So we call it Vmax, and in the lower side, we call it Vmin. And your output is basically as a limit. It is your maximum swing you can get the output. When you transmit a signal, there is this thing called power amplifier. And power amplifier is the last element before antenna. So this is your transmitter. And this signal goes to your receiver, to another friend, and you have low noise amplifier, right? So this part is transmitter. You transmit through power amplifier. And what you want to do is you want to transmit a huge power. Why? Because this signal is going to a base station, and the base station might be 50 kilometers there. You want a high swing at the output, but your swing is limited. It is limited by your transistors inside. You're limited by this voltage supply. It's limited by, if you are using resistors, it's limited by the resistors. In actual systems, you don't really use resistance, you use inductance. Like, let's say you apply a signal and your output cannot go higher, but it's clipped at this part. It wants to go more, but it cannot go more. This is called slew rate. Slew rate is a non-ideality. We don't want it. We want output to appear as fast as input appears. Also, we want at the output, we want to see a swing as much as we can, but it cannot. These are some kind of limits of Opamp. This shows it very nicely how or why the Opamp swing is saturated, basically clipped. You apply input signal. So this is your input signal here. It's something tiny, right? Just like real life. This is a transfer characteristic. We have a certain region, you can amplify this input signal nicely. Why? Because you don't get into saturation. You don't get into a region that you see these non-ideality. And if you get out of this region, let's say you applied a much bigger input, right? Then correspondingly, voltage input, this is the transfer characteristics, this linear curve. So this voltage input will correspond to a voltage out. So when we were here, basically when we were here, it will correspond to here, right? But when we came to this peak, well, the peak is, this is the input. The peak tells you, hey, now we saturated, so we cannot go further. This one is the amplifier characteristic curve. This one is two different inputs to show you, how the inputs can be different amplitudes. And the corresponding, x-axis, putting it into the characteristic curve, you get the output. Now, we can understand this. Output is defined between two regions, like lower region and higher region. So this is VSAT, this is minus VSAT. So your output cannot go above this, clipped. It wants to go there, but it cannot, clipped. Same here, it wants to go there, but cannot, it's clipped. You lose the signal at that point, right? So this becomes non-linear. You don't want non-linearity. You want a circuit to be in the linear domain, okay? And linearity is very important, both for power amplifiers, okay, right off before the antenna, and it's also very important in the low noise amplifier for some other reasons. Both at the transmitter and both at the receiver, these amplifiers should be very linear. The other non-ideality is output resistance. There should be a output resistance here at the Opamp, and that output resistance ideally is 0, this one, but in a non-ideal case, there is actually a resistance here. And I told you, if the Opamp is not ideal, then you gotta have its characteristics, right? And then when you do the characteristics, you do nodal analysis at X, you do nodal analysis at Y, and then you can, get the formula of transfer function, V out over V in, including A zeros, including R out. There is bandwidth limitation, which I mentioned to you. Opamp's gain is not fixed over infinite bandwidth. It comes to a point, then it starts to drop. And due to this, I mentioned internal capacitances. That's why this drop happens. And we define this characteristic with Laplace. Like, this is DC gain of the Opamp, which we call it A0, like in an open loop condition. At frequency omega 1, this becomes 1 plus J. magnitude-wise square root 2. And basically the 3 dB frequency. The V out becomes 1 over square root 2 less. Like basically you are losing your voltage here. You lost it 1 over square root 2. Here you lose more. Here you lose more. But this frequency is called cutoff frequency because you lose 1 over square root 2, 20 log 1 square root 2, minus 3 dB actually. This bandwidth limitation, due to the capacitance. Now, as I mentioned to you, this was the open loop gain. Now we connect this Opamp in a feedback. And as I mentioned to you, feedback, you lose gain. You compensate gain to make it more stable. So this was the open loop gain A0, which is the gain of this single Opamp. And now you applied some feedback structure, as I mentioned, and this is the V in, blah, blah. Let's ground this, for instance. So, and this is V out. So due to this feedback, now you have this gain, okay? And hey, I drop my gain from A0 to A0 over this, like this much. And actually that enables you to boost your cutoff frequency from F1 to another frequency, like which is this. And this is interesting because now we understand there is some kind of magical constant, and that magical constant is bandwidth times gain. So here in the first case, this was your first curve, the orange curve. You had a gain of A0 and you have a cutoff frequency of F1. So let's call the gain times bandwidth A0 F1. And now we put the structure into feedback, and the new curve, less gain curve, became this. So the gain is this, and the cutoff frequency is this. And when you multiply these two terms, you realize that it's also A0 F1. You lose the gain, but you boost your cutoff frequency. As you can see, these cancel. And this is called gain bandwidth constant. So amplifiers have this gain bandwidth constant. The more you feedback it, basically the more you provide a portion of the output to here. That means you increase your feedback. So if you apply this feedback much more, you lose gain because you subtract the signal from the input. This is V in. And you lose gain, have a much higher bandwidth. So that's why we also apply feedback. It provides a higher bandwidth so that we can hold a lot of different frequencies. This is a nice way of thinking. This frequency is a function of some kind of time constant, 1 over RC. Always these cutoff frequencies are represented by 1 over RC. The cap charges, cap discharges, that creates the poles and zeros. And here F1 is caused by kind of a capacitance in your structure, in your way deep down circuit. And this cap sees this equivalent R, and it creates this cutoff frequency. If F1 is small, that means cap is big, right? That cap. Well, if that cap is big, that takes a lot of time to charge out, which makes sense because that's what this structure is saying. If F is small, then cap is big, so I cannot really host a good output signal. But if the C is small, then that means your RC constant is small, and then you'll see a super fast output compared to the previous case. Like the caps will charge super fast. Your slew rate is affected by the cap. This is your input, ideal amp. You want to see the dashed lines. In the non-ideal practical, you'll see some kind of rate charging, like exponential, right? This is your input, and of course you multiply with a minus 8. This is your output. And if we take the derivative of this output signal, it will be this. And if you take the maximum value of this, it will be the peak A times VE times omega. So this is your output signal's maximum peak value it can reach. That should be smaller than your circuit slew rate so that your circuit can host this input and output. Okay, this is circuit dependent, S0, and this is your input frequency or output frequency and gain dependent, because S0 is your basically top threshold. Your circuit tells you, hey, I can host slew rate less than S0. You apply input, you get an output. Well, that output derivative, which means slope, right? So for instance, this is input, let's say. This is your output, desired output, but your desired output won't be a sinusoid because it will actually have a less slew rate because sinusoid has a huge slope. Your circuit, design circuit, slew rate will host your input and output signals. If your output signal slope is less than slew rate, yeah, it's great. If it is not, your circuit will not function well. It will not host your input well. Even you don't apply any signal to the op-amp, even you ground this, there is still some kind of a voltage there, and that's called offset voltage. These offsets usually arise from the input stage mismatch. And that means these mismatches basically create non-idealities. And even you don't have any input voltage, you get to see a voltage at the output of the op-amp. It happens due to these transistors. There are mismatches and there are unwanted variations that cause this voltage. So you can see the effects of DC offsets. Just short this Vin, and when you short the Vin, you just see this offset voltage, and this offset voltage will appear at the Vout. Just short this, make it 0. It will appear as 1 plus R1 over R2 is the gain of this closed loop times V offset. This offset is important because now there is no input, but actually there is an input, even you don't apply it. And now this offset gets integrated, and you don't want it, right? Like this offset now becomes much more, like through this cap. This offset shows up here. This creates a current, and it creates a current as well, right? Because plus wants to mimic minus. So, and this offset in integrator shows up much more compared to just the amplifier, because now we are integrating kind of a signal that we don't want. And similarly, the last non-ideality is the input bias current. Just similar to the offset voltage, there is also a current leaking from these nodes. So if you draw the actual structure, there are transistors here. Normally there is a current flowing here, IB, IC, and this current leaks here, and we cannot, prevent this. And this is called input bias current, IB1 and IB. And it is basically modeled a current source from input to the ground. We also call it leak current because this leaks from the input. And similarly, these bias currents will show up at the output. For instance, we model this as IB1, IB2, and these currents will just show at the output as a voltage. The out becomes a function of IB2. So you do a nodal analysis and you see that this IB2 shows at the out, and it creates a voltage that we don't want to have. That is an unwanted signal. So if you have an amplifier, you want to see something like XVin, right? Make it to have a linear. But if you have some other terms, XVin plus A plus B, like a constant voltages, we call this offset voltages. We want to design a system that is a linear function of the input.